Hey, welcome back, everybody. So today we want to prove that classic result from elementary school that if 3 divides the sum of the digits of some number, then 3 actually divides that number. So the first thing we want to do is recall the definition of divides. So we're going to say let a and b be integers. A divides b, denoted a divides b like this. If there exists some integer c such that a times c equals b. And so, for example, 5 divides 30, since 5 times 6 equals 30. There exists some integer c such that a times c equals b. Okay, so now on to our main result. So yeah, we said if 3 divides the sum of the digits of a number, then 3 divides that number. So for example, let's say we have the following. So let's say we have 3 divides. I'm not super creative here. So let's say 3 divides 24, since 3 divides 2 plus 4. So 3 divides this number since 3 divides the sum of the digits, right? And this is the same thing as saying 3 divides 6, which we know is true. So that was our quick divisibility test. And so, for example, I know that 3 divides 123, for example, since 3 divides the sum of the digits. Now, typically that's a rule we just sort of take on fact when we're younger, sort of in our pre-formal days before we learn proofs and we learn to question such things. But today I think it's a good time to prove this. And in order to get there, we're going to need to prove a little lemma, a short little result that we're going to use in our main proof. And so the proof of this lemma will be by mathematical induction. So this is a great opportunity to practice that skill. And so the lemma says the following. So this is our little lemma. So 3 divides 10 to the n minus 1 for all natural numbers n. So you pick any natural number n, place that here, and you're going to have a number that 3 divides. Okay, so let's prove that this is true for every natural number. So I'm going to say proof. And let's say we proceed by mathematical induction, right? That's the technique we want to use here. And the reason why we want to use mathematical induction is because we have a sequence of statements involving natural numbers. So yeah, we proceed by mathematical induction, specifically on n. Okay, so mathematical induction on n. Okay, so first we need sort of a name here. So let's let P of n be this statement. So let P of n be the statement. Three divides 10 to the n minus 1. And so you can see for each natural number, I get a new statement. Okay, so the base case that I want to establish in this case will be P of 1. Okay, so we want to establish that the statement P of 1 is true. Okay, so that's not too difficult. So let's see what happens. So 3 divides 10 to the 1 minus 1. Well, that's certainly true because that's 3 divides 9. And so that's true. That's a true statement, right? 3 divides 9. Okay, so we've got our base case established. Now we want to move on to the inductive step. And so I'm going to say let's fix some k. So let n equal k. And we want to assume that P of k is true. And our goal is to show that P of k plus 1 is also true under this assumption, right? So let's say we wish to show that P of k plus 1 is true. Okay, so I get to use this inductive hypothesis as much as I want on my journey to proving this. Okay, so let's see what we have here. So we have, let's see, where do I want to line this up? Well, let's line it up here. So we've got 10 to the k plus 1 minus 1. That's ultimately what we want to say something. We're hoping that 3 divides this. Okay, so how do we get there? Well, we're going to use auxiliary terms. That's when you use a useful form of 0, you add and subtract the same quantity. We're going to see in a moment why that's useful, really because our inductive hypothesis will pop up and we're free to use that as much as we want. So here's my useful form of 0. And you can imagine why this is useful, because if I factor out a 10 here, I'm going to get a 10 to the k minus 1. And that's going to allow me to use this. Okay, so using auxiliary terms. And now sort of just grouping the two terms together. So I'm grouping these terms together. I'm grouping these terms together. Now for these two terms, I can factor out a 10. So we've got times 10 to the k minus 1. And then 10 minus 1, of course, is 9. Well, this is very nice, right? So by our inductive hypothesis, we know that this is divisible by 3, right? We said right here, assume P of k is true. What is P of k? That 3 divides 10 to the k minus 1. So I know that 3 divides this by assumption. So I'm going to say, well, by our inductive hypothesis, let's say that 10 to the k minus 1 equals 3j for some integer j. That's going to allow me to rename this 3j. So I've got 10 times 3j plus 9, but you notice now that both of the terms are divisible by 3. So we can go ahead and factor out a 3. So if I factor out a 3 here, I'm going to have 10j left over. And then, of course, I'll have a 3 left over here. But look, I've got 3 times some integer, right? This is certainly an integer. So this is equal to 3m, where m is equal to 10j plus 3 in integer. But we've shown what we need to show, right? We've got that 3 divides this quantity, right? So 3 divides 10 to the k plus 1 minus 1. That's what we wanted to show, and we showed it. So 3 divides 10 to the k plus 1 minus 1. And so we want to sort of wrap this up and put a nice bow on this induction problem. So the thing you need to realize is I wasn't specific about k, so I just fixed some k and showed that, well, under this assumption, this happens. So since k was randomly or sort of arbitrarily chosen, then this holds for every natural number because there is no special condition put on k. So I want to say that. So, well, since k was arbitrarily chosen, we have, by mathematical induction, that 3 divides 10 to the n minus 1 for all natural numbers n. Okay, and that's our little lemma. We're going to use that when we prove that if 3 divides the sum of the digits of a number, then 3 divides that number. So look out for this idea in that proof. Okay, so on to our main result. So this is the whole goal of the video. So our main result so we're going to say, well, if 3 divides the sum of the digits, I'm going to write that this way. So the sum from k equals 0 to n, this is some finite sum, of a sub k. So if 3 divides the sum of all the digits of a number, then 3 divides that number. And I'm going to write it in this way. Think about this in terms of like digit place value and not multiplication. Then 3 divides that number. So this is the number in the 10 to the nth place. This is the number in the 10 to the n minus first place, etc. Again, not multiplication. This is to sort of suggest place value. So if 3 divides the sum of the digits of a number, then 3 divides that number. Let's prove that. Okay, so we've got a conditional. Of course, we want to assume this and show this. So for our proof, so let's assume that 3 divides the sum of the digits of some number. We want to show this, right? This is our goal. Okay, so keep in mind, place value is the key. So let's write this out here. We'll work with this, expect to use this and maybe our lemma from before, and hopefully we can show that this is divisible by 3. Okay, so let's see what we have here. Okay, so this is our number. These are just all the digits. Okay, so I want to rewrite this in terms of place value. So just before I do that, this is similar to the idea that if I have, let's say I've got 352, that's the hundreds place, that's the tens place. So hundreds, tens, ones. I can rewrite this as 3 times 10 squared plus 5 times 10 plus 2 times 10 to the 0 or 1. So this is exactly what I'm going to do, this kind of idea here. So using place value. So using place value here, so I can write this as, well, this is a sub n, but times 10 to the n. So this is in the 10 to the n place. Okay, so this is in the 10 to the n minus first place. And so on. And we keep going down the road until we get, so this is 10 to the first, a sub 1. I could write this as 10 to the 0 times a0 if I wanted to. And why not? Let's do that. I'm not going to need the 10 to the 0 in a moment, but I could certainly write it in this way. Okay, so using place value, digit place value, we can rewrite any number in this way. And so now we're going to use that powerful idea of auxiliary terms. We're going to insert useful forms of 0. That's totally legal. You can add 0 all you want, but it's going to be very helpful, and we'll see why in a moment. Okay, so here for the first term, I want to, let's see what we want to do here. So we want to take this, and we want to subtract an and add an. Okay, so here's my auxiliary, here are my auxiliary terms, useful form of 0. And if you're careful, you can see why you want to do that, because if I factor out an an from these two terms, think about what our previous lemma told us, right? So that's actually quite useful. Right, if I factor out an, I'll have 10 to the n minus 1, which is divisible by 3, right? So that's actually quite useful. So we're going to use that same sort of trick of using auxiliary terms for each of these, except for that one. We won't need it here, but we'll need it for all the rest here. Okay, so more of the same. So we're going to subtract an minus 1 and add an minus 1. We'll do the same thing here. So we have 10 to the n minus 2, an minus 2. We subtract that, and we add. That's our useful form of 0. We're going to keep doing this. So we've got minus a1 plus a1. And here I could just think about this as a0. I actually don't need to think about this as 10 to the 0. So here I just have a0. And we'll see why in a moment, why that's fine. Okay, so lots and lots of auxiliary terms. And so now we're going to just start to factor. So for these two terms specifically, right, so right here, I'm going to factor out an an. And notice I get 10 to the n minus 1. That's really nice. And then this can just hang out for a bit. We're going to play the same game here. So let's go ahead and factor out a sub n minus 1. We've got 10 to the n minus 1 minus 1. So that's from here. And then this term can just hang out. Same thing here. Factor out a sub n minus 2 from these two terms. We've got 10 to the n minus 2 minus 1. And this term can just hang out. Plus dot dot dot. We continue in this way. Same deal here, right? So just factor out a1. We've got 10 minus 1. This term can just hang out. And this term can just hang out. Now, this is a finite sum, right? This is not infinite, so we can use the commutative property of addition. We can order switch all we want. We can scoop these up in convenient ways. So let's scoop up all of these. Okay, so we'll write these. And then after, we'll scoop up all of these terms here. All right, so this is going pretty well so far. So plus dot 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 plus a sub 1, 10 minus 1. And then, so this scoops up all of these. Now I want to scoop up all of these. So I have an plus an minus 1 plus an minus 2 all the way down to a1, a0. Well, here we've got a nice pattern. We can represent this in summation notation, and here as well. So my index I will start at 1, and it's going to end at n. That makes sense, 1 to n. We've got a sub I times 10 to the I minus 1. Plus, we need to describe these. So let's use maybe k for the index. So we'll say this starts at k equals 0 and goes to n. So my index k goes from 0 to n. And this is a sub k. So you can take a moment to sort of convince yourself that we've scooped up all of these here. And we've scooped up all of these right here. Well, by our previous lemma, right, we know that this is divisible by 3 because each of these is divisible by 3. And so far by factoring, the sum will be divisible by 3. So this is divisible by 3 by our previous lemma. And by assumption here, right, this was our assumption. So assume that 3 divides this. So by supposition, this is divisible by 3. And by our previous lemma, this is divisible by 3. So this is equal to, let's say, 3y plus, 3x plus 3y for some integers, x and y, by previous. So I'm sort of sweeping in there the definition of divides. So yeah, assume that this is equal to 3x for some x by definition of divides from our previous lemma, and that this is equal to 3y by assumption. Well, this is equal to 3 times x plus y, which is equal to, how about 3z for some integer z. But if you follow this back, this says that 3 divides this, right? We have the definition of divides. So yeah, just by definition of divisibility, 3 divides the number. Again, this is not multiplication. This is to sort of imply place value. And so that proves, that establishes that old rule from elementary school that if 3 divides the sum of the digits of a number, that 3 divides that number itself. So cool.